Hello everyone, welcome to Probability and Statistics for Data Science. I guess I should start by explaining the title of the video. When I was a student, I was extremely confused about the definition of random variables, and I think the reason is that the mathematical definition of random variables is very detached from the way we deal with random variables in practice. I'm going to try to clarify this in the video. The title is inspired by an awesome paper that I will link in the description. Okay, let's get to it. Today we're going to talk about discrete random variables. The goal here is that we want to model uncertain quantities that can take a finite number of values, or at least values that we can map to the natural numbers. Okay, so 1, 2, 3, 43, 134. Okay, not uncountably infinite. We'll get to that when we talk about continuous quantities. So some examples of uncertain quantities that we might want to model include the number of students attending my next class, for example. It might be 60, it might be 3. It's definitely going to be a finite number. The goals scored in a soccer game, typically also finite. I mean, in theory, I guess we could consider it countably infinite, but you know, there's going to be at most 8 or 9. Earthquakes in the San Francisco Bay Area in the last 20 years. Okay, so there could have been like 20 earthquakes, 113 earthquakes. I'm not an expert, so I don't know how many there were. But this is another uncertain quantity, especially if we want to predict maybe the earthquakes that will happen in the future, that also takes discrete values. So our plan is going to be to define discrete random variables, introduce the tool that we essentially always use to manipulate them, which is the probability mass function, and explain its properties. And then we'll see how we apply all of this to real data. The prerequisites for this material are probability and estimating probabilities from data. Like here, I want to explain the notation. So in general, in this course, we're going to refer to deterministic variables like a, b, x, y, etc. Without a tilde on top. These are values that are not random, they're not uncertain. We might not know their value, we might just want to represent it with a variable, but it's a fixed value. Okay, you can think of them as you can essentially replace them with a number. Instead of b, we could have written 5, same thing. There's going to be some other variables which we're going to call random variables, and those we're going to represent with a tilde on top. And those variables are uncertain, they don't have a fixed value. We cannot say, the random variable a equals 3. Instead, what we say is the probability that a equals 3 is 0.5. The probability that a equals something else, 23, is 0.1, and so on and so forth. And this is really important. And we want to make very clear what is a random variable and what is a deterministic variable that has a fixed value, and we use tildes to indicate that. The challenge that we're going to face is how do we define these uncertain random variables in a formal way. And what we're going to do is we're going to build upon the mathematical framework of probability spaces. In order to describe how we do this, I think the best thing to do is to just follow a simple example. So we're going to imagine that we have a probability space that represents 2 rolls of a 6-sided die. What are the outcomes? So again, when I ask you a question, my suggestion is you can pause for a moment and think about it. So the outcomes could be 2, 3, 6, 1, 1, 4, and so on and so forth. Okay, so whatever we get for the first die, whatever we get for the second die. We can represent this as a vector where the first entry would be the value that we get for the first die, let's say 3, or the first roll if you want. So we have one die and we roll it twice, doesn't really matter. And the second entry of the vector is going to be the second roll, the result of the second roll. Okay, now imagine that we want to, what we are really interested, so we have this data from this experiment, we want to characterize it probabilistically, we build this probability space, and a quantity that we're particularly interested in is the result of the first roll. That is an uncertain quantity that takes discrete values, right? It can only be 1, 2, 3, 4, 5, or 6. Now, it turns out that we can express this quantity as a function of the outcome. So remember, the outcome are the values of the two rolls. So what function are we going to use? The function is actually very simple. Okay, like as often, I'm a bit late with, sorry, I was a bit early with respect to my slides. So the key insight here is that we can represent the random variable, this variable that we're interested in, as a function of the outcome. Okay, and that's how we actually define random variables, as functions of outcomes. But let's look at the example and then I'll come back to this point. So okay, so here is the function. So remember that this guy is a vector that has two entries. The first entry contains the result of the first roll. The second entry contains the result of the second roll. We choose the first entry, boom. That's the quantity that we are interested in. Now we can just refer to this random variable when we want to refer to that quantity. This might sound a little bit strange that we're doing this with functions, and in my opinion it is. But as we will see, it's a very useful framework, and we are going to talk about its connections to how we deal with random variables in practice. So bear with me for a moment. Okay, so we call, because this is a function that maps, it's a function from the sample space to real numbers, to a discrete set of real numbers. In this case, from the sample space to the set of real numbers 1, 2, 3, 4, 5, 6. We call the possible values that the random variable can take the range of the random variable. Because if you remember calculus, functions, the space to which a function maps is called the range. Okay, that's where that name comes from. For random variables, the range is essentially the values that they can take, that this uncertain quantity that we're interested in can take. In this case, what is the range? I just told you. Okay, so the range is 1, 2, 3, 4, 5, or 6, because those are the values that can be mapped to from the sample space by the function that we have defined. We can define many random variables in the same probability space, and this is part of why we actually define random variables in this way. So for example, we might be interested in the value of the second roll. What function are we going to use there? Well, we're just going to take the value of the second entry of the vector that represents the outcomes. Imagine we're interested in the sum of the two rolls. What are we going to do? We're going to add the two entries. It's important to emphasize, and this will become more important later on when we consider multivariate distributions, that the outcome that we obtain from the probability space fixes the values of all the random variables. The random variables are just functions from the outcomes to particular values. So once we reveal the outcome, everything is fixed. So in this case, if we reveal the outcome and the outcome is 2, 3, A is going to be equal to 2, because that's the value of the first roll. At the same time, B is going to be equal to 3, because that's the value of the second roll. And C, which is the sum of the two rolls, is going to be fixed to 5. This is super important because it allows us to model dependencies between random variables. But as I said, we're not going to talk about that today. We'll talk about that later on in the course. Okay, so we usually don't deal with random variables by doing what I just did, which is defining a probability space and then reasoning with the probability space. Instead, what we do is we use something called the probability mass function, which is very reasonable. Let me tell you intuitively first what it means. Basically, if I'm interested, for example, in this die roll, I know that the die roll can take 6 values, 1, 2, 3, 4, 5, 6. So I'm going to be interested in the probability that it takes each of those values, the probability that it takes 1, the probability that it takes 2, the probability that it takes 3, and so on. That is the probability mass function. That's it. So let me define it formally. The probability mass function, P of A of a discrete random variable, is the probability that A equals to each of its possible values. Okay, so we plug in the value. For example, what is the probability that the die row is equal to 6? And we get the probability of that event. That is an event, right? And I'm going to show you a picture in a moment. You have to see that event basically is the set of all outcomes that map to that particular value. And then the probability measure will tell you what's the probability of that event. Okay? When we define a PMF, we often say that the random variable that has this PMF is distributed according to the PMF. And that characterizes the distribution of the random variable, which is its random behavior. Now, some of you might, especially the ones that are more mathematically inclined, might think, wait a minute, Carlos, like you were talking about this, blah, blah, and then suddenly you said, yeah, we have these events, and the probability measure is going to assign a probability to those events. But how do we know that? Are we sure? Because the probability measure does not always assign probabilities to every event. And that is an excellent point. It's a really good point. In fact, in our formal definition of discrete random variables, we're going to actually impose that as a condition for a random variable to be well defined. You often do this in mathematics, right? You see, things break down if this doesn't happen, let's impose it in the definition and not worry about it. So that's what we're going to do. So the idea is that if we have a function A that maps a sample space to real values in a discrete set, A1, A2, and so on, we consider the sets in the original probability space, in the original sample space that map to each value. I'll show you a picture in a moment. And we impose that those sets or those events must be in the original collection of events of the probability space. Okay, so we assume that there's a probability space. The probability space, like all probability spaces, has a sample space, a collection of events, and a probability measure. The function maps the sample space to this discrete set. And again, I'm going to show you a picture that hopefully will clarify things in a moment. Now, the probability measure assigns values to sets of the sample space, right, that we call events. If we want to know the probability that the random variable is equal to A1, then we have to consider the event that contains all of the outcomes that map to A1 or A2 or AI in general. And we need that the probability measure assigns a probability to that event, because otherwise that probability is not well defined. We cannot, for example, define the probability mass function, or we cannot talk about the probability that the random variable has that value. Okay? So we impose it in the definition. For a random variable, a discrete random variable to be valid, it has to be true that these events are in the original probability space. And this, mathematically, if you want to know the fancy term for this, this means that this function is measurable. Okay, so here is the picture. This is a very simple random variable that can only take 3 values, 1, 2, and 3. So its PMF is here on the right. Okay, so this is the PMF. The PMF tells you the probability of each of the values. And if we're looking at the original sample space, and we want to determine the probability that the random variable takes each of those values, so let's look at 1, for example, you have to go back and see what are the values that map to 1. Oh, it's that set, it's that event. Well, what is the probability of that event? And that's going to be the probability that the random variable equals 1. Same thing for 2. Okay, so we want the probability that the random variable equals 2. You have to look at all the outcomes that map to 2, and that's going to be the probability of 2. Same for 3. These are the outcomes that map to 3. It turns out that the probability measure assigns them less probability, so the PMF at that point is smaller. And when we define a random variable, what we're saying is the probability measure better assign a probability to all of those. These are called preimages of the random variable, all the events that map to each of the possible values that the random variable can take. Okay, so let's go to my reaction to all of this stuff as a student. Okay, so, I was sitting there and someone said, we define random variables as measurable functions on a probability space. And I was like, what? And I mean, the thing is that if you start thinking about the implications of this, so now imagine I want to, model the students that arrive at a class, or the number of earthquakes in San Francisco and so on. I have to come up with a probability space, design the sample space, design the collection of events, decide on the probability measure, somehow estimate it from data. What if I have like 20 random variables? Do I have to come up with a sample space such as all of these functions are measurable? This sounds super complicated. And what happens? Well, in practice, what happens is that we never define random variables through the probability space. We never build the probability space, define those functions, make sure that the preimages are measurable. We don't. Which, like when I finally understood that, like I calmed myself, but I was also like, okay, so why do you start with that, right? Why do you start telling me about these functions of sample spaces? I was just so confused. And the reason is, there's a good reason for that. I'm not criticizing it. The reason is that we need a rigorous mathematical framework to be able to define random variables and define things like dependencies between random variables. And this mathematical framework actually works very nicely. It's just that it can get really confusing. So let's get back to what we do in practice. What we do in practice is we just define random variables through their PMF. That's it. End of story. You want to know how a random variable behaves? I will tell you the PMF. We can all forget about the underlying probability space unless we want to prove something about probability theory. Okay, but when we're doing data science, it's going to be PMFs and that's it. Okay, so hopefully that relieves you from some of the confusion that I felt when I was exposed to the mathematical framework of random variables. Okay, so let's go back to these preimages because now we're going to derive some properties, some important properties of the PMF, of the probability mass function, and we're going to need to understand this a little bit in detail. So it turns out that if I consider these events that map to the possible values of the random variable, they form a partition. It's not difficult to see why they need to be disjoint, because if the random variable is a function, it cannot map the same outcome to two different values, right? So an outcome here is either mapped to 1 or it's mapped to 2, right? It cannot be mapped to both at the same time. This implies that these sets, these events, have to be disjoint. So far so good. But to form a partition, they need to cover the whole sample space, but we're defining the random variable as a function, so it is going to assign a value to every outcome in the sample space. So it's going to be so this means that it's going to cover the sample space, so these preimages are going to be a partition. Why is this important? Well, this is important because this means that we can essentially express any probability that we might be interested in with respect to the related to the random variable. We can express it with the probability mass function. So let's see what I mean by that. So let's say we have a probability space, a function A that maps to a discrete set, and we consider the preimages. Okay, they form a partition of omega. I just realized that this slide is saying exactly what I explained in the previous picture. I had the following slide in mind, so forgive me for that, and let's move to that. Now imagine, okay, within that, knowing that, hold that thought that they are a partition, because we're going to use it in a moment. Now let's consider the probability that the random variable is in a certain set, in a certain subset of its values. Because what are we going to do with random variables? We're going to talk about their probabilities. We're going to say, oh, what's the probability of rolling an even number? What's the probability of rolling more than a 3? Stuff like that. And we can express all of that stuff as a set of the discrete values that it can take. Okay, so let's say that we're interested in a particular set S of discrete values that this random variable can take. How do we go about computing that probability? And now let's be mathematically formal, because we're going to see that we just need the PMF and then we can just forget about the underlying probability space. Okay, but before we forget, we actually have to prove this. So this is the probability of all the outcomes such that the random variable maps to S. We can divide that, for example, if it's the even numbers, right? If this is the probability, the set we're interested in is the even numbers, rolling an even number. We can decompose that set into a union of the following sets, or the union of the sets of outcomes that map to each of the A's that form S. Okay, so if we're interested in the even numbers 2, 4, 6, these sets would be the outcomes that map to 2, the outcomes that map to 4, the outcomes that map to 6. We have said that those events form a partition, so in particular they're disjoint. So we can just add up these probabilities. And each of the individual probabilities is just equal to the value of the PMF there. Okay, so we're done. We can express any probability that we might be interested in about this random variable in terms of its probability mass function, so we can forget about the probability space, thankfully. Okay, we know it's still there. It's like the motor of your car or the motherboard in your computer. It's there. You don't really understand it, or at least I don't really understand them. But, it's good to know that they're there. We're not going to refer explicitly to it, as we're usually not going to refer explicitly to the probability space unless we need to do some mathematical proof. It turns out that any PMF must sum to 1. That's easy to see because when we sum up all of these values, implicitly, we're summing up the union of all of these sets that map to each of those values. And because they're a partition, that's the probability of the whole sample space, which is equal to 1. We could also have derived this from common sense. The random variable has to take a value, so the sum of the probabilities of it taking every possible value has to add up to 1. Okay, but this is a mathematical derivation. It follows from the fact that those preimages are a partition. Okay, so let's do an example. We're modeling the probability that a soccer game ends up with a certain goal difference, -2, -1, 0, 1, etc. And we think that the only possibilities are -2, -1, 0, 1, 2, 3. So it turns out that we're maybe modeling the team that is stronger. We think that it's more likely that they will win than that they will lose. Okay, and we determine these probabilities somehow from data. Okay, so now what is the probability that there's there's a difference of -2 or a difference of 2? Well, we've seen that. All we need to do is we go to those particular values of the PMF and we add them up. So in this case, that would be 0.1 plus 0.1, 0.2. We might be interested in the probability that the goal difference is strictly above 1. That would be a goal difference of 2 or 3. Probability of 2 is 0.1, probability of 3 is 0.05, 0.15. Okay, so it's really easy how you use a PMF to compute probabilities of interest. Okay, so for any function h and any random variable a, is b equal to h of a random variable? We often do this when we're modeling. We're interested in some uncertain quantity and then we're like, oh, but I'm actually interested in a function of that variable. For example, in the case of the goals, you might be like, sure, like the goal difference is interesting, but what I really want to know is how many points for the league, like maybe this is a league game, how many points is the team going to get from this game, which would be 3 if they win, 1 if they draw, and 0 if they lose. So then you have to kind of transform the probabilities that you have about the goal difference into probabilities about the points. And we're going to do that in a moment. But how should we go about doing that? Well, first we have to determine whether the function of a random variable is actually a random variable so that we can maybe define its PMF. Well, not maybe. So that we can define its PMF and reason with it. Intuitively, if A is an uncertain quantity that can take the values A1, A2, and so on, B is also going to be uncertain, right? Because you're pushing something into H what comes out is also going to be uncertain. It's also going to have a discrete number of values, which are going to be HA1, HA2, HA3, and so on. Some of those might be repeated, but they're not going to be more than A1, A2, A3, and so on. So it's also going to be a discrete number of values. Mathematically, if A is a function from the sample space to the discrete set A1, A2, A3, then the composition of A and H, which is this random variable B, is also going to be a function from the sample space to H of 1, H of 2, H of 3, and so on. So it is a function. Now we have this little caveat that we need the preimages of that function to be measurable. That means that the probability measure assigns them a probability, because otherwise the probability that B is equal to a particular value is not going to be well defined. But that actually follows automatically from the fact that A is a random variable. Okay, because we're considering these events where we consider the outcomes that map to a particular value of B, but we can just decompose that into, okay, for what A's, for what AI's or AJ's here, is HAJ equal to B. Okay, there's going to be a few of them. Then we realize that this event is just a union of those events. And those events need to be in the probability space, because the probability measure needs to assign them a probability so that A is a random variable. So if A is a random variable, this means that these guys are assigned probabilities, which then means that this guy is going to be assigned a probability. So if A is a random variable, B is also a valid random variable. And this is an example of where you want to make things mathematically precise, so you have to go back to this underlying probability space, which again is something that we never do in practice. In practice, I'm going to show you in a moment how we go about deriving the PMF of the new random variable. Okay, so let's go back to that example that I mentioned very briefly, where we're interested in the points that the team is going to earn from the game, which is 0 if the goal difference is smaller than 0, because they lose, 1 if they draw, the goal difference is 0, and 3 if they win, goal difference is larger than 1. Okay, so now what you do is you say, oh, I'm interested, and now we're going to build the PMF of X, which is this new random variable, which basically is the result of applying this function to the random variable G that represents the goal difference. Okay, so what's P of X 0? And here I like to go to the definition. The definition is the probability that X is equal to 0. And that probability is the probability that G is smaller than 0, which is the probability that G is equal to -2 plus the probability that G is equal to -1. And that probability equals 0.2 plus 0.1, 0.3. Okay, what's the probability that X is equal to 1? That's the probability that the goal difference is 0, because then they draw. That's easy, it's this guy. Okay, so it's going to be 0.3. Again, by the definition, what's the probability that X is equal to 3? It's a probability that the goal difference is above 0, because the team wins. What's that probability? 0.25 plus 0.1 plus 0.05, it's going to be 0.4. What's the probability of X being equal to anything else? 0, because that can't happen. And now we have derived the PMF of the new random variable, and you see that it's really easy. Basically, you see what's the probability of the random variable being equal to these particular values. You express it in terms of the random variable that you already have, and you use the PMF of that random variable to determine those values. And that's what we get. Okay, this is the PMF of the number of points. In practice, when we have some data, in order to model an uncertain quantity that has values in a discrete set, because this is the point of this whole endeavor, what we're going to do is we're just going to estimate its PMF, because we have just shown that afterwards, if I want to compute like probabilities of interest about this random variable, if I want to compute the PMF of a function of this random variable, all I'm going to need is the PMF of the random variable. So that's what I'm going to estimate directly from data. Nothing about this underlying probability space. So now, if you're a mathematician, or if you're really into math, you might be, but Carlos, wait a minute. how do we know there's an underlying probability space? Maybe everything crumbles. Okay, so things do not crumble. And the reason that they don't crumble is that if we manage to estimate a PMF that is non-negative and sums up to 1, we can always cook up a probability space that would be the underlying probability space. And the way we can do that for discrete random variable is actually quite simple. We just say, oh, the sample space is the values that the random variable can take. The collection of events is going to be the power set, and the probability measure is going to be the PMF itself. And I'm going to leave it to you to check that that works out, because it's really not that important. Essentially, we estimate PMFs and we'll work with PMFs. Okay, so then there comes the question, how do we estimate a PMF from data? So imagine that your observations, you have like a random variable that can take values, I don't know, 1 or 2, and you have these observations, 1, 2, 1, 1, 2, 1. What do you think is a reasonable estimate for the value of the PMF at 1? Again, pause for a moment and think. I would argue that a reasonable value is, first we need to ask ourselves, what does the value of the PMF at 1 represent? It's the probability that the random variable equals 1, right? So it makes sense to use the empirical probability that the random variable equals 1 for that, to estimate that quantity. In this case, we have 4 data points out of 6 where this uncertain quantity equals 1. So a reasonable estimate for that value of the PMF is 2/3. Okay, and that's it. That's the empirical, that's the main statistical estimator that we use to estimate PMFs, although we also do some other stuff, like in the next video we'll talk about parametric PMFs and then we'll talk about how to estimate them. But the simplest possible way of estimating a PMF is just applying empirical probabilities. So you have a data set x1 to xn, which can take values in a discrete set A. If you want to think of it as 1, 2, 3, 4, 5, 6, if we're estimating the probabilities that a die has certain takes like a die roll takes certain values. Anyways, any discrete set that we're interested in. Now the empirical mass function is essentially equal to the empirical probability that these guys are equal to each of these values. So the empirical mass function at A equals 1 would be count how many data points are equal to 1, divide by n. Okay, end of story. So we're just using empirical probabilities. Extremely simple, but used all over the place. So now we have to ask ourselves, is this empirical PMF a valid PMF? The only thing that we have to check is that it's non-negative and it adds up to 1, and then there'll be an underlying probability space, blah, 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 blah. We don't have to worry about it. Is it non-negative? It is, right? These are empirical probabilities. It's a non-negative number divided by n. It's going to be non-negative. So yes. Now we need to see whether they're going to add up to 1. So we're adding, remember, we're adding the PMF over all its possible values. That's 1 over n times the sum from I1 to In of this indicator variable, which is equal to 1 if xi is equal to a and 0 otherwise. And here we see that we can actually change the order of the sums and basically just add from 1 to n this sum, which is the sum of the indicator variable over all the possible values of the random variable. And since we have assumed that like the data points are all equal to some value in A, then this thing must be equal to what? Think about it on your own. This thing must be equal to 1. Okay, because it has to be like, there must be some A such that xi is equal to A. Some A in this big set A. Okay, I realized that one. I meant some little a in the set capital A. Okay, so basically because all of those guys are 1, you sum 1 n times, you get n, you divide by n, you get 1. So we have a valid PMF. That's good news. We can just, use the empirical PMF as the PMF of the random variable and, do some interesting stuff. If you know what a histogram is, essentially what we're doing is we're taking the histogram. So let me explain what a histogram is. This is a histogram of the die rolls that I mentioned when we were explaining empirical probabilities. In that video, actually, I wanted to show you the die that I used. Okay, this is the die that I used. Now I remembered to bring it. I forgot it in the previous video. So anyways, remember, like me and my daughter, we rolled this die like 60 times, and these are the counts that we obtained. We obtained 10 ones, 12 twos, only 2 threes, and so on and so forth. When we are computing the empirical PMF, essentially what we're doing is we're taking those counts and we're normalizing, dividing them by n, in our case 60, to obtain an estimate of the PMF, okay? As in the case when we're talking about empirical probabilities, we need to ask ourselves, when we're estimating this stuff from data, is it going to be like a very precise estimate, or is it going to be an exact estimate? Let's start with that. And the answer is, of course, not. To demonstrate this, I did a simulation where I said, okay, imagine the die was perfect. This die is obviously not perfect. We'll come back to that when we're talking about hypothesis testing. But imagine that you have a perfect die. So I took the computer and just simulated it with a true PMF that looks like this. Okay, so all the values are equal to 1 over 6 of the PMF. 1 over 6 of getting a 1, getting a 2, and so on. What happens if I do 60 rolls and I compute the empirical PMF? What am I going to see? I'm not going to see a good approximation to the true PMF. Okay, so this is one instance. I did this again, I got this. I did this again, I got this. We're going to talk a lot more about statistical estimators, how to analyze them, when are they going to be very precise, when they are not precise. I just want to always, follow up with a word of caution when we define one of these objects, because here, again, we're not in the realm of probability theory. When things are exact, you define something, it's equal to something, end of story. Here we're in the realm of statistics, where things are messy. We're saying, okay, we need a PMF for this thing that we need to model. Let's do what we can, okay? It's statistical modeling, it's data science, it's messy. So we're not going to get the exact estimate, even if there was a true PMF underlying the data. Okay, so to finish, we're going to see how to model a real data set using a discrete random variable. This real data set, well, the goal of this data set is going to be to model the streaks in consecutive free throws. Okay, so the data, so what are free throws? You're in a basketball game, someone fouls you when you're about to shoot, or in some other situations, and you're allowed to shoot free throws where no one bothers you. So it's quite like a controlled, repetitive thing, and you can see whether they go in or not. And I took a data set, which I will link in the description, which contains 3,000 free throws shot by Kevin Durant in the NBA. And those free throws are separated into streaks. Okay, and each streak basically is the number of free throws that were made until he missed one of them. So the data essentially look like this. So maybe he made 2, then he missed, then he made 4 in a row, then he missed, then he made 17 in a row, and so on and so forth. That's what the data looked like. That's what the data looked like. So now there are actually, let's think about how we compute the empirical PMF. There are 42 streaks of length 2. So can you tell me, tell yourself, because I won't be able to hear you, but what is the PMF, the empirical PMF, at 2? What we do is we apply empirical probability, 42 divided by 377. Okay, so the probability that a streak has length 2 is around 11%, according to this data. Okay, so this is what the empirical PMF looks like, and as a data scientist, you should, or just as a common sense person, you might ask yourself, how accurate is this? I would argue that it's a little bit strange that 7 has a smaller probability than 11. That sounds weird, right? Because it seems more difficult to score 11 free throws in a row rather than 7. So unless something strange is going on there, that might be caused by, just noise. We'll explain what I mean by noise in much more detail later on. It's also maybe, surprising that these probabilities would be exactly 0, and then suddenly we get a non-zero probability here or here, right? So if he's managed to make like 52 free throws in a row at some point, it's unlikely that the true probability of him making 50 is 0. Okay, so there we can actually see that this is probably inaccurate because we're not observing enough data. Okay, so what have we learned here? We've learned the mathematical definition of discrete random variables, and hopefully we have learned to not be afraid of it because it makes sense, it's important. We just ignore it almost completely when we're doing data science. We just use the PMF instead, but it's good to know that it's there. We only need the PMF. We've learned what the probability mass function is, how to use it, how to derive the probability mass function if we have a function of a random variable. And then we have seen how to estimate the PMF from data. Because at the end of the day, that's what we're going to do in practice. Thank you very much.